be running the probability session. And just a disclaimer that some of these materials were taken from the CS 109 course, which some of you are currently going through. But hopefully it gets you up to date with all of the foundations you need for your projects later on. So first we should ask maybe, why are we covering probability given that this is supposed to be a workshop on medical AI? So as James has pointed out with his linear algebra and calculus, maths and probability really is the backbone of the AI and machine learning revolution. And it's sort of really the staple tool and the essence of everything that we're doing. So if we want to learn more about all of these concepts here, we'll need to understand the maths behind it, at least at an intuitive level. So here's the roadmap for what we'll be covering today. So first I'll go through some fundamentals, and hopefully most of this is revision from high school. Apart from maybe Bayes' theorem, which might be new for some of you. And then we'll go through some distributions, random variables, and finally go on to how probability looks in machine learning with applications such as MLE and MAP. So just to start off, how do we define a probability? Does someone want to give us a short definition? Yeah, the likelihood of something happening. It's a way that we sort of define and handle uncertainty. And when it comes to an official definition, this is like our formal definition for probability. So it's the ratio of events to non-event outcomes when we increase our number of trials to infinity. And these are some other important definitions. So our experiment is just the setting of our outcomes, such as rolling a six-sided die. Sample space is all the possible outcomes of an experiment, and an event is sort of any one of those, so a subset of any one of those. And just to begin, you may have seen these sort of rules in a different context or under different names, but formally they're known as the Kolmogorov axioms. So an axiom is just some statement that we take just at face value, and we don't need to sort of prove that that's true. So our first one is that all probabilities are between the numbers of 0 and 1. Second is that all the outcomes from an experiment must belong to the sample space. So the total of the sample space will be 1. And 3, if E and F events are mutually exclusive, then we can simply add their probabilities to find their cumulative probability. Based on those 3 axioms, we can sort of derive these 2 identities. The first one is sort of like the complement probability. So the probability of something not happening is just 1 minus the probability of it happening. And secondly, that if any event is part of a subset of a larger sort of set, then its probability must be less than the probability of that larger set. So pretty simple stuff. I'm going to go through probability of OR events. So what does this mean? Basically, what's the probability of like A or B? And how do we sort of work this out? So this is all dependent on whether those events are mutually exclusive. And mutual exclusivity is when we have no outcomes that can fulfill both of these events. So written in stat notation, that's E intersect F is null. So if we do have 2 mutually exclusive events, then we can simply just add those probabilities. So that's the same as our third axiom. And if they're not mutually exclusive, well, then we have to account for double adding that intersection point. So if you can see here, if we were simply add the 2 probabilities, we would be accounting for that intersection point twice. So we just need to subtract it off. Yep, should make sense. And second, we'll talk about conditional probability. So this is simply the chance of an event happening given that some other event has happened. And once we condition on that second event, the only outcomes that are now possible are, of course, the ones that exist in the world in which that event has happened. And this is a useful concept because it helps us to update our beliefs in the face of new evidence, and we'll see how it's applied later on when we go through Bayes' theorem. And just to note that you can also condition on multiple events, so you just chain them together. Now about independence. So two events are independent if you, by knowing the outcome of one of the events, it does not change your belief about whether the other events will occur. So for example, if you were to flip one coin and you get heads, that doesn't tell you doesn't influence the probability of heads when you flip another coin. And our sort of definition for this mathematically is that probability of E given F is equal to just the probability of E. So that conditioning on F hasn't really changed our beliefs in E happening. And the way that we calculate the probability of two events happening, this depends on whether they're independent or not as well. So if they are independent, then we'll do something called product, and if they're dependent, then we use something called the chain rule. So product is sort of like what it sounds like. You just, for events that are independent, you can just multiply them together to find their probability of them all happening. And when it comes to dependent events, so we'll use something called the chain rule, and in this case, I'll just start with an example where you have two events. So for two events which are dependent, E and F, to find the AND probability, you would do the probability of E given F, and then multiply that by the probability that F happened in the first place. And yep.
Yeah, this is a question. So would it also be like probability of E times probability of F given E? Is that the same as that? So
as in, could you do it the other way around? So F given E and then probability of E? Yeah, you could do it the other way around. So you can sort of interchange it. And then if you look at the more general rule, yeah, so you just start with the first one, probability of E1, and then what's the probability of E2 given that E1 happens? What's the probability of E3 given that those happened, and so on. So you just keep chaining it along. Yep, next we'll go to the law of total probability. So for any event, we'll take E, for example. You can sort of split the probability of E happening into two sort of subsets. So either it happens and F has also happened, or it happens and F has not happened. So it's just a way of splitting up the probability instead of thinking of the problem in two different ways. So put using this set notation. So a probability of E is equal to the probability that E's happened given F, and then multiplied by the probability of F. And then also you have to add the probability that E happens and F did not happen, and multiply that with the probability that F did not happen. So yeah, pretty simple stuff. This is the more general statement of the law. So what you have to make sure when you're using this is that when you split up your sample space, you're doing it into mutually exclusive events. And those mutually exclusive events have to cover the entire sample space. So you can't have any sort of like possibilities falling through the cracks. The whole thing needs to equal the total probability. Okay, and now we'll move on to Bayes' theorem, which might be maybe the first piece of new content. But it's a very, very useful formula and something that we use a lot in machine learning. Essentially, it allows a way for you to convert the conditional probability of something into the other direction. So if we look at the formula, it's very easy sometimes for you to know like the probability of A given B. But what if you wanted to know the other way, probability of B given A? This allows you to convert between the two using that formula. I think James has something to say about this as well.
Oh yeah, so I think Bayes' theorem is too cool to just be covered by like a couple slides. So I'll just go through an example like with a really medical context. So let's say the prevalence of breast cancer is 1%, right? Sensitivity is 93%, specificity is 90%. These are numbers just not like real life numbers obviously, just for the example. But what do you think intuitively, like just gonna guess, what's the probability of someone with a positive test? So someone has a positive test, actually has breast cancer. Do you want to use a mic to throw out some numbers, like what you think it might be? Just looking at the pretty good sensitivity and specificity numbers. Lewis. Yeah, just guess a number. Like seriously, what's the
Don't think about it too much.
1 in 50? Okay. Yeah.
I was gonna say like 10%.
10%. Any other guesses? So the number that we're guessing for is actually the positive predictive value, right? So that's the probability that someone tests positive actually has breast cancer. And this is actually really cool with Bayes' theorem, because let's say that B is breast cancer and E is testing positive on the screening mammography. So what's the probability of B in medical terms? Yeah, exactly, the prevalence, right? So that's what's the probability that someone has breast cancer, just selected, let's say, from the general population. Now, what about B given E? Yeah, good. So it's when someone actually tests positive, that's E. If they know that they test positive, what's the probability that they actually have breast cancer? Right, and then this is goes really well with the formula of B given E is B and E over the probability of E. So what's the So that's basically the sensitivity. So what about, so probability E given B then? Oh, wait, did I say the probability of, oh, sorry. The probability of B given E isn't the sensitivity. So this is a positive predictive value, right? This is someone actually has breast cancer. So someone actually has breast cancer after they have a positive mammogram. So that's what we're going to find out. And that's why Brian labeled it's called the prior and the posterior. So this is another way to think of Bayes' theorem. So on one hand, this is a formula that allows you to flip E given B and B given E. But on the other hand, it's a way to update our beliefs. So let's say someone comes in and you want to know if they have breast cancer or not. The prior is your best guess, right? That's the prevalence of breast cancer. So we want to know, after they have a positive test result, how that's going to change our belief whether they have breast cancer or not. So it's almost like a scaling factor to our pre-existing belief. So E given B, that's a sensitivity. So someone actually has breast cancer. What's the probability that they actually test positive? But what's the probability of E then? Yeah, good. So this is what's the probability of someone testing positive overall? So people who test positive, that can be two camps, right? So this is from the general population, and what this is this is the law of general the total probability that Brian was talking about. So what does E given B times the probability of B give us? So if you were to change E given B as a fraction and then multiply that with B, what would you get?
True positive. Is that what you want?
So it's the probability of E and B, right? So remember how the law of total probability is this plus that. So the total probability is what we call this this E right here, for example. So this is the probability of E and F, which is this part, as well as the probability of E and not F, which is that part. Does that make sense? So this one you kind of have to think of as a formula, because the formula of E given F is E and F over F. So the F will cancel each other out. Does that make sense without like writing it down? So why this part is same as E and F? Okay. And this part is basically this area, right? So that's E and not F. So that's what we're doing here, which is the probability of E is E and F. So the people who have breast cancer and test positive, and people who don't have breast cancer but still test positive. So basically everyone who has breast cancer, everyone who tests positive, they can either have breast cancer or they can test positive and not have breast cancer. So that's what the law of probability is, total probability is so helpful, because it allows us to take one probability and then break it out into kind of two compartments, right? So this is people who test positive and breast cancer, test positive but no breast cancer. So this is the sensitivity, right? The probability of testing positive when they have breast cancer. And this is the false positive rate. So this is the people who test positive when they don't have breast cancer, which is 1 minus the specificity. So we can actually plug that in to see how that updates our belief on someone's probability of breast cancer. So what is this right here, E given B? What numerical value is that?
93, right?
Yep, so someone with breast cancer actually tests positive. And what about the probability of B?
1%.
Yeah, so that's that. And what about this part?
Is it the same?
It's actually the same thing, right? Because this is all this is trying to say is that people who test positive and have breast cancer, same thing. What about this part? Hmm?
Is it a 5.1?
Yeah, 0.1, really good. So specificity is 90. So this is a false positive rate. So it's 1 minus the specificity times the probability of so what's this? Yeah, 99%. So this is the probability that someone doesn't have breast cancer, right? So once we plug that in, we get something like this, and it gives us 0. So about 8%, which is actually crazy though. So you guys guess like really well. But then I was thinking like, okay, what's the point of a test? So that means that what this means probabilistically is that if these are the stats, which are pretty good stats, that means that only like out of 100 people that test positive, only 8 people actually have like breast cancer, which is crazy. That means that other 92 people, we're just like scaring them for not much reason. But I guess, yeah, this is a really, I think, cool math way to think about all the probabilities and puts into perspective in our context. So this is another way to write it. So yes, one way you can think of it as flipping the probability. That's really useful for machine learning. But also another way, kind of just as a philosophical understanding, is actually moving this B on the other side of the fraction. So what we're doing is that we're thinking of this as a prior belief, right? And we want to know how, when someone does come in with a new test result, how that changes our understanding. So that's what this is. So that's the probability of the original belief. This is just, imagine this as one block that either scales your belief up or scales your belief down. And your new belief, it will be the probability of B given E. Yeah, I just thought this was really cool when I learned it, when I learned the Bayes theorem, and yeah, very yeah, thanks, Brian. But yeah, this is a summary. And in terms of likelihood and marginal, that doesn't really make too much sense. But understanding the prior and the posterior. So prior is just before you get your new information. Posterior is after you get your information. I think this is really cool.
Yep, thanks, James. Yeah, it is really cool. And it sort of helps you reason sometimes about why screening tests at the population level sort of exist for certain diseases and don't exist for others. And perhaps has something to do with sort of our positive predictive value and the sort of attributes of the test that we have statistically. But yeah, it's really, really useful. And all the different components of Bayes' theorem also have their own sort of names. So we talked about the prior, the posterior, and sort of the update is that probability of E given B, or also known as like the likelihood. And then that probability of E underneath, we call the normalization constant, or marginal as well. Yeah. So with that in mind, that's all of the fundamentals that we have right now. And we can sort of walk a bit more into sort of distributions now and random variables. Bit of a summary of everything. And before we move on, I thought that we'd just throw in a bit of a problem that you can solve using the tools that we just talked about. So maybe we'll just break for like 5 minutes and you guys can sort of work together and try and work out the answer for this one. Might need some pen and paper.
Did you pause the recording? Pause the recording?
Oh yeah, okay guys, we can come back now. I think everyone's pretty much solved it. So just go through the first one. So the way we can solve it using sort of the things that we talked about. So you can first split up the total probability using the law of total probability and then chain rule each side and just substitute in your values. So you get about 0.029 as your answer. I know you can do it like in a more intuitive, easier way, but this is just like to practice using the rules. And then for our second one, you can also use Bayes' theorem for this. So in this case, we already know sort of a probability of E given M, and we want to know the opposite, so the probability of M given E. And plugging in all our values, we're able to solve for that, so around 0.69. Great, so now we'll talk a bit about random variables, which may also be a bit of revision, but a random variable is essentially some variable that probabilistically takes on a value. So this could be the total number of heads after flipping 3 coins. So that could be, let's say, 0, and you'd have a 1 out of 8 chance of that happening. Or it could be 1, and that would be a 3 out of 8 chance of it happening. So this is a random variable, as in it can take on any of those values with a given probability. And for every random variable, we have something called our probability mass function. So this is something that essentially graphically maps out those probability distributions. So on that left side, we have that uniform looking graph. That's the chance of getting like 1 to 6 on your single 6-sided die roll. And on the right, you have the probability mass function for the sum of rolling 2 dice. And just to note that these PMFs can also be represented using equations. And some important things to talk about are also expectations. So for every sort of random variable, we also have an expectation as to what value it would take on. So this is essentially just the weighted average of our random variable. So we'd take the sum of all of the values that our random variable can take on, weighted by the probability that they take on that value. Does that sort of make sense as well? Yeah? Next up is variance. So variance is one of our key measures for the spread of a random variable around the mean. And it's actually cool to take a look at the intuition behind this as well. So if we look at so that top and the below sort of equations are equivalent. But if we look at the top, the variance is essentially just the average distance of any sample from the mean. And if we look at this term over here, so look at the inner term. So x is just any sample from our data. So x minus, and this is our expectation. So in other words, our mean. So we're looking at the difference between any sample from the mean. And can someone tell me why we then square it?
So we get a positive value because of the distance.
Yeah, well, yeah, so it's to account for, let's say some of the data might be below the mean and some of it might be above the mean, and we don't want that sort of their position to affect our calculation because they would cancel out otherwise if we have negative and positive values. So we square all of it, and then we take the expectation or the average of it. So essentially, this is how we get to the intuition that it's the average distance of any sample from the mean. And standard deviation is just another way that we sort of represent spread. So now we can talk a bit about discrete distributions. And before that, let's talk about parametric random variables. So we know what random variables are now. Parametric random variables are sort of those distributions that are common and they're well studied. And if you're able to recognize that your data fits into one of them, you're immediately able to just inherit all of those pre-derived, pre-studied attributes. So one of the examples of this would be like the normal distribution. If you find that your data fits a normal distribution, you could plug in the mean, you could plug in your standard deviation, and from that you'd be able to derive the entire curve and sort of take all of the properties of that normal distribution. So we're going to look at some discrete examples of that first. So the first is a Bernoulli, and this is the simplest kind of parametric discrete random variable. So this can either take on a 1 or a 0, and usually we'd have 1 signifying success and 0 signifying failure or just some other event other than success. And this can be, for example, whether a coin flip hits a heads or hits a tails, and whether sort of a server crashed or whether a neural network has correctly predicted some outcome. So wherever there's a binary sort of output, we can model it using Bernoulli. And as long as we've recognized that our data fits a Bernoulli distribution, we can then take all of these sort of properties from it. So the way that we notate a Bernoulli variable is by just like the x tilde burn, and then we put in our parameter. So whatever's in that bracket's a parameter. It looks quite similar to a function that we would write in Python, but that p is all we need to take on everything else. So the p is the probability of success, or x equaling 1. Yeah, and from that we'll know how to derive everything, including the expectation and the variance. Next one we'll take on is the binomial. So essentially a binomial is a series of independent trials of an experiment where each of the probabilities of success for each trial is notated as p. And essentially you can think of it as a bunch of Bernoullis stringed together. So this could be like if you flipped a certain number of coins, so like n coins, and see how many heads appeared. And similarly, all of these properties you can take on once you've discovered that your data takes on a binomial distribution. Yeah, and just a note, so this is the PMF, or the probability mass function equation. We haven't really talked about this yet, but does someone want to maybe give us a refresher on what this is? Yeah.
I don't remember the formula.
Oh, no, that's okay. Yeah, it's a combination. You're right. It's a combination. So essentially, you can also say n choose x. So this is the formula for it. And yeah, important for you to just like know what it is. But don't worry too much about deriving sort of combinations, permutations for now. Yep, so we just have a short little exercise here. It should be pretty simple. Actually, you guys can just shout out the answers once you've worked it out. Yep, 6. Yep, and you can do this intuitively, but using like sort of the properties we talked about, the expected value is NP. So 6 is the answer. Next, what's the standard deviation? You probably need to know the the formula for it. Yeah, you know the formula for it. So once you worked out that it's binomial, you can just sort of plug in all your values. So for binomial, you can see there are actually two parameters that we need, like that, which is unlike the Bernoulli. You need both n and you also need p. And once you have those two, you can work out all the other properties. And now we would talk about what is the probability that 10 or more locations have outbreaks. And the way you do this is using that, so we go back earlier, it's using that PMF equation that we talked about. So you can work out the probability that there are 10 outbreaks, and then work out the probability that there are more than that. So every single one, 11, 12, 13, etc., and sum them all together to get this. Yep, so that's it for discrete distributions, and now we'll talk a bit about our continuous ones. So when it comes to continuous distributions, I'd like to start with a bit of an analogy first. So imagine you're running to catch a bus, and you know that you'll arrive at 2:15 p.m., but you don't know when the bus will arrive. So you want to sort of model this problem and think of the arrival time in minutes past 2 p.m. as a random variable known as t, so that you can calculate the probability of waiting more than 5 minutes. So the problem here, right, is that we can't really think about the probability of an exact moment in time. For example, we don't know how to work out the probability that the bus will arrive at exactly 2:17 and, let's say, 11.235, etc. seconds. We we're used to thinking in those discrete variables, but when we move to continuous, this way of thinking no longer really works. So how could we sort of approach this problem? One way is that we could sort of create these little buckets in time. So we create these different categories, 5-minute chunks, and we work out the probability of the bus arriving within any given chunk. But again, this is not that precise in that we can't tell like what's the difference in the probability of it arriving at the start of that 5-minute chunk or the end of the 5-minute chunk. So what's something that we could do? Yeah. We could make the bucket smaller, that's right. So if we go into 2.5-minute chunks, we would have a bit more precision. But again, we run into the same problem when we want to know like the probability at the start or the end of each of the buckets. So we could just keep going. And eventually we'd end up with a smooth looking curve just like that. So this is what's known as a probability density function. So for every continuous variable, instead of thinking about PMFs, which are our probability mass functions, we can think a bit more about, so they're now known as PDFs for our continuous variables. And the way that we find the probability in any range for one of these variables is we just need to integrate between the range, so A and B. So if we look here, we would integrate between 15 and 20. There are some implications for this kind of modeling though. So we just need to remember that when we sum the entire curve, the probability still needs to sum to 1. And when we ask about the probability of any one value, the probability will equal 0. Because clearly, if you were to think about like what's the probability the bus arrives at, let's say 12 seconds and 0.1234 forever, that single sort of value doesn't take on any probability. It only sort of has significance when we talk about a range of probability. So our first, now that we've moved more into continuous random variables, our first sort of continuous distribution is the uniform. So in the uniform distribution, we have a given range, so our two parameters are alpha and beta, and we have the same probability of an event happening within every value between that alpha and beta. And these are just some of the properties of the uniform distribution. You don't really have to memorize any of these, but it's just useful to know that these are all like available once you know your distribution. And of course, we have our normal distribution as well. So this is also known as the Gaussian. And it's sort of generated from the summation of many independent random variables. And it's very important because it often occurs in nature and often occurs in contexts where we want to model.
Just a question.
Yeah.
For the uniform one, so if you take a point in time or whatever,
Yeah.
does that give you a number or is it still undefined?
No, so if you were to integrate between like the same point, right? So you're just going at any one point, that that probability would still be 0. Yeah. So you need to give it a range for any like significant probability to come out. Yep, and these are just some of the properties of the normal. No need to memorize again. So the thing with all of these distributions is there really are sort of hundreds of distributions, and we haven't covered like even like a tiny amount of them, right? There's a lot of other important ones out there, but the important thing is to know sort of how to recognize, like once you have a data set that fits one of them, how do you go about getting those properties? So you need to be able to work out, like if my data is distributed this certain way and it looks like a normal, I can go and find all of these properties. That's the main thing. It's working out how to use sort of distributions that you've never seen before. Yep, so with that covered, now we'll just talk about two things, correlation and covariance, before we move on to machine learning. So covariance is sort of it's a quantitative measure which captures how two variables change with each other. So an example would be if two variables are independent, then their covariance must be 0 intuitively, because they don't sort of have any interaction with each other in terms of their likelihoods affecting the other likelihood. But just a warning that this is not always the case when you take it in reverse. So just because two events, or like two sort of variables have a covariance of 0, that doesn't always mean that they're independent. And correlation is just another measure we use as well. So this is about the linearity of two variables, whether they are correlated or not. Just says whether like they have a linear relationship. So negative one correlation would mean they have a negative sort of linear relationship. 0 would mean that they have no linear relationship at all. Yeah. So that covers our two first categories, and now we'll just take a look at how some of these things are applied into machine learning. All right, so for all of the distributions that we have just seen, we had sort of parameters that we needed to plug into them to be able to work out all the other properties. So we encounter a problem sometimes when we just have data and we don't know how to work out those parameters. So we need to sort of estimate them using parameter estimation. So just a reminder, yeah, these are the parameters that we need to plug in. So for Bernoulli, we need P, which is the probability of a success. We haven't covered Poisson today, but let's say uniform has A and B, which is the range in which the probabilities exist. And then for normal, we need our mean and our standard deviation. So when it comes to parameter estimation in machine learning, we'll talk about two main algorithms. So the first one is something called maximum likelihood estimation, or MLE. And the second one is maximum a posteriori, which is MAP. So MLE is more of a sort of frequentist approach, whereas MAP is something that we call a Bayesian approach. So it will make use of that Bayes theorem that we looked at earlier, and you'll see a bit more about like what I mean exactly. Just to note that both of these approaches also assume that our data is independent and identically distributed, meaning that each data point belongs to the same distribution. So first on MLE, the central idea behind MLE is that given some set of IDD, or independent identically distributed samples, we're able to select parameters which make this observed data the most likely. So our philosophy is that we want to maximize the likelihood of our observed data. So what does this mean? When we say we want to maximize that likelihood, what is the likelihood? So the likelihood is our PMF or our PDF, depending on whether our data is discrete or it's continuous. And we'll notate this like this. So F and then big X equals X is just like the probability of one of our our value taking on our data taking on one of the values, and this is our parameter. So our chosen parameter equaling sort of theta is a general sort of term for parameter. So all of these in this table, we'll notice that all of these are sort of like equal to like notated as theta. So yes, put out into plain English, probability that X takes on a certain value given that our parameter value, like given the parameter value which I've chosen. And we really want to just try and find the correct parameters which maximize the likelihood of our data. So if we think back to the rules that we had during the foundational session, once we know that our data is sort of dependent, we can simply find the product of all of those data points, and that becomes our total cumulative likelihood. So we move from this sort of single likelihood, and we sum all of the data points to find the so we've taken a bit of a look at this before. So this is just the sum of all of these data points, and that is our total sort of likelihood for all of our data. And this is something that we call our likelihood function. So this represents the likelihood of all our data, and what we want to do is now maximize that. And just to note that the parameter here is, like this is all dependent on our parameter. So we're just going to find the parameter that maximizes this. And we do this using something called argmax. So argmax is essentially sort of an algorithm that changes what's in the domain, so in this case the parameter, to maximize the function that it's given, so our likelihood. And theta hat is what we use to denote like our best theoretical possible parameters. So these are the ones that give us our best likelihood. Just a note as well that we like to use log likelihoods. So instead of just using this plain likelihood function, sometimes we'd like to log it instead, and that just makes it a lot easier to compute. So when we have the log here on the outside, we can sort of move it into the product notation, and this product notation will now become a sum notation. And that's because of our sort of our log laws here. So the log probability is simply just when you apply that natural log function to your likelihood. And the importance of this is, for example, if you have a very small number, a very small probability, it's very difficult for your computer to store that because it's storing in float representation and not in an exact representation. And it's also a lot easier for you to compute sort of addition instead of multiplication, especially when you're dealing with parameters that are sort of in the hundreds of thousands or even the millions. Yep. So yes, this is our MLE summary. So our goal of MLE is to find parameters which maximize the likelihood of our training data, and we do this by first working out the distribution of our data and knowing what parameters are needed. Then we create our log likelihood function, and then we sort of run argmax on it to find that best set of parameters. And I know we haven't actually talked about how argmax works yet. We'll talk about that later, and also I think Kwal will talk about it as well during Thursday and Friday sessions. But does anyone have any questions about MLE first before we move on to MAP?
Yeah, I have a question. So just in a higher level overview, like so if I'm understanding right, so the different distributions.
Yeah.
We have our data, we don't know what distribution it will hold. So step one is to work out what our distribution is going to be, and then we figure out what parameters we need to find out from our distribution, from our data.
Yeah.
Right? And then what's the point of a likelihood function?
Yes, so once you've worked out like what your distribution is, remember all of those distributions need your parameters, right? Yeah. But like you don't know what exact parameters will give you that right curve. Yeah. So you just know it's a normal, but you don't know what mean and what standard deviation would give you the curve that best fits your data.
But like, wouldn't you get that from your data? As in like, because in order for me to figure out what distribution my data needs to be, like, aren't I like finding out the parameters from the data first and then modeling and then seeing what it would be?
Oh no, I think like you can do it if you have like a smaller set of data, but you can't always do it. Like sometimes, I think for normal, it's pretty easy to do, but you can't always do it for like other distributions as well.
Oh, so it's like more like we take our data at face value and they're like, oh, it's probably going to be this distribution.
Yeah. A lot of times people will assume like data is normal, for example. Yeah. Or like they'll be given data and they'll roughly know like what distribution it is. Okay. But then you have to work out the parameters that actually like fit that curve.
Right.
Yeah.
And then that function is likelihood.
Yeah, and you work that out by constructing your likelihood function and then sort of optimizing that likelihood function. Yep, any other questions? Nope, okay. So that's MLE, and we'll talk about MAP a bit as well. I haven't gone into too much depth on MAP, but it's just important to know like there's another school of thought when it comes to parameter estimation. So this MAP is focused around the goal of finding the parameters that make the most, that are the most likely given the data. which sounds pretty similar to MLE, but this is the difference. So MLE finds the parameters that make the data the most likely. MAP finds the parameters which are most likely given the data. So it's the switching of the conditional here that makes the difference. So data given the parameters, and then parameters given the data. And these are just some differences, and there are sort of two approaches that are used in different contexts, but when it comes to MAP, you're able to account for prior knowledge that you might have on the problem, and that actually weighs in on when you're calculating your most likely parameters, whereas MLE has no room for that sort of prior knowledge. Generally, MLE is better when you have a large data set and you're able to calculate it, but MAP can be used on those smaller data sets as well. And MLE is usually less computationally expensive than MAP, which may be more complex. So just a brief sort of bird's eye overview of MAP. It's derived using Bayes' theorem here, and we sort of convert it to a log likelihood function. So if we look at it here, this top part looks very similar to the Bayes' theorem here, and we sort of just like expand it out. And then this is how you convert it into a log function. You don't actually have to know how to like do this yourself by hand. Like we have plugins and methods and everything for that. But just so you know, like roughly how MAP differs from MLE.
So just a question about that.
Yeah.
So for MAP, would you define what sort of distribution you think your data is then? Because it needs to figure out, it finds parameters for my data.
Yeah, it does the same thing. So you would need to, like, again, the steps are that you need to find the distribution, work out, like, what parameters you need. And then you'd find the actual values for those parameters using MAP.
Okay.
Yeah. Yeah, so argmax is like that magic step that we talked about at the end, but we haven't talked about how we actually do that. So we saw a bit about this during the calculus talk as well. So when it comes to optimization, how do we find sort of the maximum point here? Someone just remind us. Yeah. You differentiate, set it to 0, and then that's how you work it out, right? So this is pretty simple to do when we just have a plain graph like this. But it becomes a lot more complicated when we have those thousands or hundreds of thousands of parameters. So we introduce a bit of something called gradient descent, which I think some of you probably have had exposure to before. But this is an example of when we map out, so a 3D graph, which means we had 2 parameters. We're trying to find that bottom point. And I know that earlier we talked about sort of maximizing our likelihood. You can really think of gradient descent as either, like, it could be ascent or descent, depending on whether you flip the graph up or down. But just like by convention, we do gradient descent. So that log likelihood function we talked about earlier, we just turn it into a negative, and now we're doing gradient descent. So this is the whole idea of gradient descent, is that we start off with sort of these random parameters, and we know that they're not the best parameters. We want to find what parameters minimize our loss / maximize the likelihood if we flip the graph upside down. The loss is the difference between sort of our prediction and the actual true value. So when we have training data, we would know like the true value, and we would know our predicted value from the model. And we want to measure that loss and then sort of minimize it. So backpropagation is something that Kwa will go through during Thursday and Friday, but this is sort of the algorithm that's at the heart of training these machine learning models. We start by randomly initializing our parameters. So something that we'll talk about more later as well is random seeds. So random seeds are essentially those random starting points. Along our, this is something called the loss landscape. Along this landscape, we're going to select random points to start at. Those are our random parameters. And we're going to make a prediction, which is our forward pass. Once we've made our prediction, we can work out how off we were. So we know our true value, we know our prediction, that's our loss. And to calculate our loss, that's where we employ MLE or MAP. So this is to calculate our loss function / our likelihood function. So that's how MLE and MAP sort of fit into the whole training process of neural networks. Once we can calculate our loss, we now need to sort of work out which direction to move to make sure that our loss is minimizing. And we use that calculus to do it. So we'll differentiate. So we have to use partial differentials because we have so many different parameters. And then we work out which direction is the steepest, and we keep moving in that direction, taking steps down that curve until we reach a minima. And that's sort of the heart of backpropagation, which Carl will go into detail on Thursday. Yeah. Just as a bit of an example, I thought I'd go through a CS demo. So this is taken from the CS 109 workbook, which you are welcome to take a look at after as well if you want to sort of supplement your learning and brush up on this stuff. But given our data here, let's have a visual representation of how MLE looks like. So this graph, we know it's Gaussian, and we know where our data points are plotted. We just need to work out what parameters give us the best fit. And we have a few things here that we can calculate at each time. So we have our likelihood, we have our log likelihood, and then we have the best log likelihood that we have. And now we're just going to try and change our parameters to see how that changes our likelihood. So here's an example. So for our mean, we're going to move the mean up 1. And we see that there was a change to our likelihood there. So if we go down 1, we're at 399. We go up, it's 398. It's 398 still, 397. And as we keep going up, eventually we start like falling off and we start going back down. So this was our best sort of likelihood that we found, right? We want to try to make it as less negative as we can. And when it comes to the other parameter, we're going to keep shuffling this up and down as well to try and find which maximizes our likelihood. So if we go down here, we see that our log likelihood is going in the wrong direction. We want it to sort of minimize. So we're going to keep going up, and we notice that we're starting to get better results here. And we're still going, and eventually we've gone off. So now we are less likely than we had before, and this is our best likelihood. So now these are our optimal parameters, and that's how we found it. Is it always negative? I think it's negative just because that's how like the log works. So when we plug in a value that's like the probability is below 1, between 0 and 1, it would just become negative. But yeah.
So if it wasn't negative, what would you be trying to get it to?
If it wasn't negative, like if you had applied like negative to it, so now it's positive.
Yeah.
Yeah. So then you're just trying to sort of minimize it. Yeah.
Just a question. Like,
Yeah.
I remember in high school when we learned like normal distribution stuff. There's like a sweet spot of like your sample size needs to be at least more than 30 or something for it to have for it to obey like normal distribution rules.
Yeah.
So that also applies here, right? So like for each distribution, there should be like a sample size you're aiming for. Let's say we're using clinical data. We need like a healthy sample size.
Yeah. I guess if you have too small of a sample, it'd be really hard to know what distribution it belongs to. Yeah. So yeah. And there's also something called like central limit theorem, which is like when, you might have seen it before. Yeah. Like you have all these independent trials and then they'll all, like no matter what distribution they are, they eventually sum to a normal distribution anyway. Yeah. So that's pretty cool. But you need a good sample size anyway. So yeah, that's everything we covered actually. It's a pretty short lecture. But does anyone have any questions before we wrap up?
So like in practice, how do you see us like applying like this in the like for the especially the latter part when you're like, modeling? Yeah.
Oh, how do you apply it? Yeah, so when we are actually training our own models, we need to construct a loss function, right? Loss function is another way of saying like a likelihood function. And the way that we construct that likelihood function is by using like one of these approaches. So probably MLE. So you would first get your data, you'd construct your likelihood function, and then using that you'd be able to carry out your gradient descent after. Yeah.
So
Yep.
for when we're trying to find out the loss function and stuff, we use the MLE, and
Yep.
then you see the log, the negative stuff, right?
Mm-hmm.
So if the maximum one, which is the best outcome, is like negative 200 something, and it's not good enough, so we just continue the loop. Is it like we use another value or something, go down the gradient,
Yeah,
try
yeah.
another value, and then use that value to find the maximum again, and try to find the lowest, the negative, like the smallest negative number. Is it? So we just keep on like doing the same thing.
Yes,
The
so you're
whole
talking about this process. Do we have to do this multiple times? Is that what you
Yeah.
mean? Yeah, that's right. So when we're talking about sort of smaller models, we can afford to carry out this process and randomly initialize over and over again. So let's say we found like a minima, and we have no way of knowing if that's the absolute global minima, right? Because we can't graph it out when it's like thousands of parameters. So in that case, we might want to reinitialize and restart the process again to see if we can get a better result because we're starting at a different point. So for example, if we started, like, you can see that there's two sort of minima here. If we started like over here, we might end up in this ditch. But what if this ditch is over here is better, right? We wouldn't know unless we had started somewhere over here and then moved down into here. So that's a chance that we might want to take, but I think for bigger models, you might not be able to do that because it's too expensive to do it again. So sometimes like you just have to take what you can get.
Right, you know how like you're trying to get to the lowest point?
Yeah.
Like your algorithm, I don't know what the algorithm is, but the point being is to get to the lowest point.
Yeah, yeah.
Will it at any point be able to climb upwards to try to get lower, or will it only try to get lower?
No, only try to get lower.
Okay, so
Yeah.
the moment you enter the ditch, you're fucked. Like you're
Yeah, yeah. So if you were in this ditch already, you can't just climb out of the ditch and go into this
yeah,
one.
So there's
Yeah.
no room for like, okay.
Yeah, so that means that's why it's really dependent on where you initialize at the start. That's why you need to, yeah. It's important to randomly initialize. And I think Kwa will talk about it as well. So you can ask him more detailed questions if you like, yeah. But yeah, that's it for now. And there's more to come tomorrow. So just before we end off today, I think let's just give some feedback and then we'll let you go for today. Thanks.